the previous video, I covered about PMS, and in this video, I will be covering about the topic through PDF. So let's begin. Okay, so continuous random variable takes value in uncountable sector, like in intervals. Okay, so the PDF is not a probability, it's a density, the probability per unit length. To get the probability, you integrate the PDF over an interval, which is given to you. Now, CDF. CDF works identically to discrete case like probability of x less than equal to x. But now it is smooth, not a staircase. So what we will do, we just integrate from one point to another point. Moving forward, this is the formula like integrating from one point to another point. And this is the function and this much only, right? Now, an integral over a zero width to integral is zero always, even if f of x is large or f of x is smaller. Okay, what does it in simple language? If we take the integral point of the simple line, it would be zero. Simple. Next is CDF for continuous RV. And okay, this is the formula only written here. From minus infinity to infinity, it would be 1, and it should be greater than equal to 0. Simple. And this is our common formula to get probability. Always integrate from A to B. Right? Now, TDF. TDF F is continuous everywhere. There's no jumps, only like no jumps like discrete. Okay. So F is non-decreasing, and f of minus infinity is equal to 0, but f of plus infinity is equal to 1 here, as you can see in the graph. Now, fundamental relationship, what is that? The PDF is derivative of CDF, okay? As you can see written here, f of x is equal to differentiation of this CDF. Now, wherever the derivative exists, this is continuous analog of PMF. PMF is jump size of CDF. Okay, you can also remember it as like PMF is equal to jump size of the CDF. Now, computing probabilities from CDF, we can see this of the these are just formulas. Hmm. Okay, so this you can see by yourself. Moving forward, this is the example given here, which is like saying um, uniform from there's x which is uniform from 0 to 3, equally likely to be anywhere from 0 to 3. So how you will represent it as like from f of x equals to 1 by 3 from 0 to 3. Otherwise, it's 0 like that. And how you will verify it? So just integrate it. You will get the integral as integrated from 0 to 3. You will get integral as 1. And how you will write the CDF function for it? Just simply that f of x is equal from minus infinity to x, f of x dt. Just differentiate it, okay? Like, no, integrate it. So it would be 0 for less than 0. It would be 1 for greater than 3. And it will be x by 3 from 0 to 3. Okay, now uh, this was the example of uniform distribution. Moving forward, the non-uniform distribution. It is simple this function effect which is 2x from 0 to 1. Otherwise, it's 0. So how you will verify it? Just integrate it from 0 to 1 simple. And for the CDF function, just integrate the value and you will get the answer. Now moving forward, the quantile function. They were engineered the okay, this is like instead of mapping an x value to a probability, the inverse CDF maps a target probability back to an x value. Okay. Now these are just differentiate between discrete and continuous random variables. This we have already discussed, so you can see only thing is like endpoint sensitivity. In it is strictly matters in discrete because we have to uh, because we have to integrate. It's a staircase jumps that's why. And in this continuous, it does not matter at all, and it's a smooth curve. Simple. In this, we just sum it. That's why we need discrete points. And in this, we just need to integrate over the interval. So endpoint doesn't matter that much. Now the pitfalls like traps where we can make mistakes. is that fx is not a probability. The PDF value at a point has no direct probabilistic meaning. Like f of x equals to 5 at some point is perfectly valid. Only integrals of f give a probability. And treating fx as p of x equals to x is the single most common error when moving from discrete to continuous. Okay, second thing is like fx can exceed 1. So the constant of integrating of f is equals to 1, not f is less than equal to 1. So a PDF concentrated on 0 to 0.1 with the f of x equals to 10 is valid. This is like you will think that the f of x is probability, but it is just a function. So next thing is like PDF is a continuous but not necessarily differentiable everywhere. The PDF is the derivative of the CDF, but the CDF might have non-differentiable points. So at those points, f is technically undefined, but can often be assigned any value since it's a set of measure of zero, right? Then there's one more point like endpoints don't matter for continuous random variable. This I already told you in previous slide, but it matters for discrete. Okay. Uh, Next is like mixed distribution exists. Like any random variable can be partially discrete, partially continuous also. Like take example of insurance payout. It's exactly zero with probability of 0.3. Otherwise, it's continuous from zero to infinity. Okay, so it's neither pure PMF nor pure PDF. So you need CDF as it is only the common thing between PMF and PDF. So now this is where major theory earns its keep. Okay. Now improper distribution. Sometimes the integration of F is negative. Example, uh, certain uninformative priors, like these are improper prior distributions. They can still yield the valid posteriors after conditioning. Okay, so it but it must be handled carefully. So just remember this point also. Now, why we are studying this? What is the real world ML connection of this topic? Okay. So this is like continuous output models like regression predicts the real valued output. It implicitly assuming a continuous distribution after Gaussian on residuals. Okay. Second thing is like normalizing flows. Explicitly model a PDF by transforming simple distribution to an invertible neural network. So use the change of variable formula of the PDF is used here. Third is like there is a term KD, kernel density estimation. It is non-parametric way to estimate function from data. So it places a small PDF like a bump kind of thing at each data point and sums it up, right? As you can see in this graph also. Then there's probability calibration. It means like evaluating whether a model's continuous confidence score actually corresponds to a valid PDF or PMF. Like it's very much critical for reliable uncertainty quantification in deployed models. Okay, so that's all for this video. Next video will be about the joint distribution. So we'll see you there. If I made any kind of mistakes in this video, you can just comment me down. Thank you. Bye bye.